Drop that. Sure. Are you going to give a presentation first, and then your student will go out to you?
Yes, I will do the first. And as you said, I will give a very brief introduction to my group and what do we do.
Okay. Okay. Let's start it. Good morning and good afternoon, good evening, everyone. And today is my great pleasure to introduce the two speakers today. And the first one is Dr. Shuo, is my old friend. And he's a pioneer in conducting multidisciplinary research for imaging centered medical data and analytics, in particular the AI in healthcare. His current research is focused on the development of AI systems to solve the most challenging clinical and fundamental data analytics problems in radiology, urology, surgery, and rehabilitation and cancer, and with emphasis on the innovations of the learning schemes. And Dr. Lee has a significant amount of influence and research reputation internationally. He's a committee member in multiple high influential conferences and societies. He's most notable for serving on the prestigious board of directors in the MICAI Society from 2015 to 2023. And also he's the chair of the general chair for the MICAI 2020 conference in Singapore. He has over 200 publications, acted as the editor for 6 Springer books, and served as the AE for several prestigious journals, including the medical image analysis. Throughout his career, he has received several awards from the GE Virus Institute and the National Organization. And the second speaker is the Mr. Zhang, and he's Dr. Lee's student. And he obtained his master's degree from the Department of BME at Western in 2020, and a bachelor degree in the Northern Western Polytechnical University in 2018. And he has published several papers in the highly referenced journals, conferences in medical imaging analysis. And now it's your turn.
Thanks a lot, Professor Zhu, for your great introduction. Can anyone help me, allow me to share my screen?
Yes.
I cannot share screen.
You could.
Now I can. Okay, now I can. Can you guys see my PowerPoint? Sorry, the PDF?
Yes.
Can you see it?
Yes, we can.
Okay, thank you very much. Again, thank you, Professor Zhu, for the introduction. Thanks everyone for coming. It's really a great pleasure to present here. For reinforcement learning, we are actually still a learner. We have been doing medical image analysis for a very long time. Recently, we started to work on the reinforcement learning. We have found that this is a great tool for our recent research. We have achieved multiple results, which Zhang is going to share in detail. But I'm going to, before that, I'm going to share with you briefly my group and what research we do. So my group is called the Digital Imaging Group of London, and our university is called the University of Western Ontario. The Chinese name is very confusing, Xi'an Daliue Daxue. It's not in Xi'an, it's not in any of the city in China. It's actually in London, but this London is not the famous London you know, it's London in Canada. So as you can see from this map, this is New York City, and this is London. This is the Canadian-US border. So London is a city in Ontario, Canada, and it's very close to the US-Canada border, surrounded by 5 lakes. A very beautiful city, and welcome to London if you have the chance to visit. My group is called the Digital Imaging Group of London. This group is support out with a very recent initiative in Canada where we connected all the major hospitals in Canada, especially in Ontario. So the major archiving center is in London. As you know, in Canada, the healthcare is paid by government. So government has a great leverage point where in Canada, all the major hospitals share data. So this is a great scenario for big data analytics. That's where our Digital Imaging Group of London started. We started at 2006. And that's where all the hospitals start to go to digitalized. And start from day one, I started this group, Digital Imaging Group of London, where I was a GE scientist. From day one, our group is multidisciplinary, multisectoral, and highly collaborative. I was a GE scientist at that time, and then I become a faculty. So even at that time, I was a young professor in the university. I had a student, I had grants, and we had a very productive environment. In this environment, we have people from multi-sectors, from industry, from healthcare, from academia, and even from nonprofit organization. And so that we work together and focus on the most challenging problem in healthcare and how do we apply the machine learning or artificial intelligence to solve it and make the life easier for physician, for patient, and for hospital administrators. Over the years, we have been working with quite a number of industry, hospital, clinician, and other collaborators. So we have been working with almost all the major healthcare providers, Philips, Siemens, GE, of course. And we also work with industry like IBM. So in fact, our first big data project was originally sponsored by IBM Cloud division. And for the research we do, hospitals is our best friends. So in London, Ontario, Canada, which is a major city for healthcare. Actually, we have the highest density of healthcare providers in Canada. We have, it's a very small city. We have only 300 to 400,000 populations, but we have 6 hospitals. And we have been working with these 6 hospitals. Then we start to extend our collaboration to the hospitals in the States and the hospitals in China. Now, we have been working with a lot of colleagues in different hospitals in different continents for various projects. We have been working very closely with clinicians, many of them from radiology. At least we worked with 45 clinicians before. At least 30 of them made a solid contribution to be the co-author of our papers. We also work with other basic science researchers from various of disciplines, medical physics, computer science, imaging, bioinformatics, biomedical engineering, and they all become co-author of our papers. We have a team of great trainee, which we are very proud of. Now, many of them, because of the visa, cannot come. But before the COVID time, we had over 16 trainees, 4 postdoc, 10 PhD students, and 3 master students. Over the years, the Digital Imaging Group London, my group, has become a training hub for many talented people. We are very proud of this trainee, and they have been very productive. As some of you may know, 2015 is a time that I left the GE and joined the academia, and I still lead the Digital Imaging Group of London. Since then, we have published at least over 70 journal papers, mostly in those prestigious journals like PAMI, TMI, Media, transaction of neural network and the learning system. We have published at least 40 journal levels conference papers in the MICAI, CVPR, all those top tiers of conferences, all thanks to the great trainee we have. We also win various awards. They're not major, but it's a recognition for great work our students do. Today we have the honor to let one of our representative student, Mr. Dong Zhang. He is a really great student. He recently defended his master, so a master thesis now. So he's a Master Dong Zhang now. And for last 2 years, he has published 2 journal papers in the Medical Image Analysis Journal, which is the very high impact journal in our field. The impact factor is over 11. And he also have a multiple co-author paper, which is fantastic for a master student. So let's welcome Mr. Dong Zhang for his wonderful presentation. Dong, I'm going to change the sharing to you. Now you can share.
Yeah, I can. Okay, so can you see my screen?
Yes.
Okay. Okay, thanks, Dr. Li, for your great introduction. It is my honor to introduce my studies in my master's and applying deep reinforcement learning in medical object detection and segmentation. Today's outline is following. Firstly, I will introduce the background. Then 2 projects we completed. And finally, I will move on to the summary. Medical object detection and segmentation demonstrates the location and the boundary of the desired object, such as lesions and organs in these examples, which is essential in almost all computer-aided diagnosis systems, such as visual-aided diagnosis, clinical parameter quantization, and surgical planning. Therefore, automatic medical object detection and segmentation significantly reduce radiologist burden because they free radiologists from the tedious repetition of manual delineation, improve the diagnosis efficiency due to the much faster processing speed of computer compared with humans, increase the diagnosis accuracy because compared with humans, computers never get tired, so that their results are always objective and reliable. As the most prevalent method in automatic medical object detection and segmentation, deep learning, or DL as we know, has promoted this field development greatly, such as prostate segmentation and skin cancer detection in these examples. But it still faces several challenges to obtain accurate results in some tasks. As the bottom figure illustrates, DL may get false positive results caused by the strong interference from the background tissues, which have similar appearances as a target object. DL may be unable to get results due to the similar pixel intensity between the target object and the surroundings. Last but not least, DL may lose details and get inaccurate results due to the severe color imbalance between the target object and the background. Deep reinforcement learning, or DRL, has great potential to facilitate DL methods to achieve better performance. As we know, the working principle of DRL is to employ an agent that self-explores the task environment by directly observing the current task state, selecting actions to transform the task into the next state. In trial and error, the agent learns the optimal strategy to approach the target gradually, as well as automatically gets the target and the reward. Therefore, given a medical image, like a radiologist changing the attention focusing area gradually to accumulate the certainty of evidence and then determine the desired object area. The agent in DRL self-explores the image with an attention bulb, considers the contextual dependence of these explored regions, then approaches the desired object gradually and proposes the region. This proposal, as the red box indicates, eliminates the interference from background, facilitates DRL method to focus on the object area and then to extract object-specific features, so that DRL methods can achieve higher detection and segmentation accuracy. Based on the above background, in this study, we leverage deep reinforcement learning to develop computer-aided tools for medical object detection and segmentation tasks. We adopted DRL to address vertebral body detection and segmentation and outperform state-of-the-art DL-based methods, thereby improving the accuracy of aided diagnosis. Moreover, we adopted DRL to address non-contrast agent-enhanced liver tumor segmentation and regular DL-based methods are hard to deal with, thereby avoiding the injection of contrast agent and providing clinicians a safer solution to make liver tumor diagnosis. In the first project, we proposed sequential conditional reinforcement learning for vertebral body detection and segmentation by modeling the spine anatomy. Vertebral body detection and segmentation are indispensable pre-steps to assist radiologists in diagnosing spine-related diseases. As these examples show, we not only can visually provide radiologists with vertebral body information, such as the shape to diagnose a vertebral fracture, but also can indirectly assist radiologists to obtain other parameters and make further diagnosis, such as assisting the measurement of vertebral body height, the grading of spondylolisthesis, and the angle measurement to predict the RSTV. However, it is remain challenging to get accurate results. For instance, the vertebral body-like architectures and the tissues in the background cause false prediction, while the similar appearance of other vertebral bodies leads to the false category identification. The imbalance of vertebral body classes causes some vertebral bodies may be missed in the segmentation. To address the above challenges and get accurate vertebral body detection and segmentation results, we propose sequential conditional reinforcement learning. Because of the spine anatomy, as displayed in the left figure, vertebral bodies present an S-shaped sequence, so that we leverage DRL to model this sequence as a special conditional decision-making process. In this case, DRL can approach these vertebral bodies along the spine one by one to propose their regions, and the location of previous vertebral body is a prior condition to propose the next vertebral body. With these proposals, as the middle figure shown, the subsequent DRL network can focus on vertebral body feature extraction instead of being interfered by the background or other vertebral bodies, thereby getting a more accurate result in the right figure. In the above conception, the goal is to propose each vertebral body region accurately. So we designed the ARL, which trains an agent to start from the previous vertebral body and then approach the next vertebral body to propose its region. It contains two innovations to propose the region more accurately: the consequence-oriented reward function and the adaptive sampling experience replay. So the consequence-oriented reward function stimulates accurate vertebral body proposals by building an exponential reward. In traditional DRL, as the left figure shown, the reward function is a step function. Namely, only when the agent reaches the target vertebral body, it gets a bigger reward, which causes this agent to explore the background TS and may approach other undesired vertebral bodies ultimately. To this, as the right figure shown, our consequence-oriented reward function exponentially increases the reward value and integrates it with the proposal accuracy, so that there always is an increasing reward gradient to stimulate the agent to approach the target vertebral body and then propose the optimal region. More specifically and professionally, the consequence-oriented reward function converts DRL's learning objective into maximizing the proposal accuracy to stimulate an outstanding performance. As the formula indicates, we found and proved that the possibility that the state S appears is negatively related to the corresponding proposal accuracy I. Here is a simple example to help us to understand this finding, where an agent approaches the target from state 1 with accuracy I1 to state ST with accuracy IT. As the agent selects different actions, the overall structure is a tree. The state with more accurate proposals requires more correct actions, thus its possibility decreases. While the learning objective for DRL agent is to maximize the sum of opportunity rewards, namely to maximize the possibility to reach the states with higher reward values. Based on the above finding and the DRL learning objective, we assume that the relation between the possibility and the states ST appears is negatively exponential to corresponding proposal accuracy IT. Therefore, our consequence-oriented reward function builds a positively exponential relation between the accuracy and the reward value. By replacing the possibility of the state and the reward in the DRL's learning objective, we can find that the objective is positively related to the proposed accuracy when the exponential hyperparameter weight is larger than 0. In other words, our consequence-oriented reward function converts the learning objective, or DRL, into maximizing the proposal's accuracy, thereby stimulating agent to achieve higher proposal performance. While the adaptive sampling experience reply improves the learning efficiency by self-select the valuable training data, particularly as the left figure illustrates. During training, the agent explores the several trajectories to approach the target. Traditional DRL blindly inputs all these trajectories or actions to train the agent, as shown in the right top figure, which causes a low training efficiency because most of them are redundant. To this, our ACR self-selects the more valuable trajectory or actions to train the agent, as shown in the right bottom figure, thereby improve the training efficiency and accuracy. We validated our method on spine image dataset. Here are some visual results. The high overlap and high similarity between the prediction and the ground truth indicates the effectiveness of our method. The numbers on each retinal body as the overlap rate between our prediction and the ground truth further demonstrates the strong ability of our method. Moreover, our method is superior to state-of-the-art retinal body detection and segmentation methods. Compared with their inaccurate result, our result is highly coinciding with the ground truth. Based on the quantitative evaluation results, compared with state-of-the-art methods, our method achieves best performance in every evaluation matrix. Here is the evaluation experiment to demonstrate the effectiveness of consequence-oriented reward function and adaptive sampling experience reply in retinal body proposal. Overall, compared with the regular reward function, the CRF improves the mean proposal accuracy by 10 to 20%, while compared with regular experience reply, the ACR not only improves the proposal accuracy, but also the training efficiency. In conclusion, this is the first study that successfully integrates DRL with spine anatomy to analyze retinal bodies, brings a new solution for spine-related researches. The result of the proposed method is superior to state-of-the-art method, which increasing the accuracy of computer-aided diagnosis. The proposed CRF and ACR effectively improve DRL performance, which promotes the development of DRL in medical image analysis. The second project, we proposed a weekly supervised teacher-student network for liver tumor segmentation from non-enhanced images. In current clinical workflow, as the picture shows, to diagnose liver tumors, radiologists usually inject contrast agents before taking MRI to enhance the image contrast and then obtain the tumor contour for further evaluation. However, the injection of contrast agents brings several side effects, as shown in the black box, such as high risks due to the contrast agent toxicity. Particularly, about 1% of gadolinium contrast agent is retained in patient's body after injection, which may cause a 10 to 15% incidence of CRN. The extra time consuming for the contrast agent administration, more specifically 40 to 120 minutes, and the high cost of the contrast agent materials. In this case, we seek a method to directly segment the liver tumor from non-enhanced images, as demonstrated in the bottom figure, thereby avoiding the use of contrast agents. This method has great clinical significance. It is safe for the patient. Also, it is quick and economical. However, it is quite difficult to get tumor segmentation from the non-enhanced image. The biggest challenge is to determine the tumor location. As the top figure shows, compared with the regular enhanced image, due to non-contrast enhancement, some tumors are barely visible, while the background has many tumor-like tissues. Another challenge is, as the bottom figure displayed, the pixel level data is limited because its acquisition requires high cost, while the relatively abundant box-level data cannot be used for segmentation training directly. So then we hope our method can exploit the box-level data to get extra segmentation improvement. To address the above challenges and achieve the tumor segmentation, we propose weekly supervised teacher-student network, which has two main parts. A teacher model learns to propose and segment tumors in a high contrast enhanced image, and the student model is guided by the teacher model to learn how to segment the tumor from the non-enhanced image. So that after training, this student model can get rid of the teacher model and handle the tumor segmentation independently. Here, the DDRL and the student DDRL are the sigma model. Their difference is DDRL develops the policy or strategy to propose the tumor, while the student DDRL takes the strategy as guidance and imitates it, thereby learning its own approach to propose the tumor in a non-enhanced image. The USSC predicts tumor masks according to the tumor proposal for every image, so that the box level data also has a pixel level tumor prediction. Lastly, the student dense unit takes the tumor proposal of the student DDRL as a prior, the mask from the teacher model as a pseudo label to train a segmentation network based on such a framework to improve the automated segmentation performance. Our innovation are mainly built on DDRL and the USSE. So the newly designed DDRL creatively improves two agents to approach the tumor and then fuses their automated proposals. Compared with the top left regular proposal, this fused proposal in the top right figure has a higher accuracy. In addition, DDRL prevents the two agents developing similar strategies and falling into the same exploration. An example is shown in the bottom left figure. So that as displayed in the right bottom figure, the two agents approaches the tumor with respective strategies, which greatly enlarges the exploration range and promotes the cooperation efficiency. More specifically, DDRL introduces the relative entropy between the two agents to achieve the above cooperation. We know that the regular DRL optimization is to maximize the opportunity reward. In our newly proposed relative entropy biased optimization objective, take the agent 1 as example. We added two terms. One is enlightened by the soft actor critic, the entropy of the policy, which increases the exploration range and avoids the agent stepping into suboptimal. The other one is the Kell divergence or relative entropy between the two policies of the two agents, which introduces the agent 2's policy into the objective, facilitating this agent 1 to develop a different strategy from the agent 2. It looks complicated, but after we simplified it, in practical implementation, the optimization objective of the state value function, action value function, and the policy function are quite clear and compact. It is easy to implement, and it effectively improves the cooperation efficiency between the two DRL agents. The newly designed USSE integrates cell-phone assembly with uncertainty to predict the tumor mask accurately. In detail, as demonstrated in the top left figure, SE can predict tumor masks for this box level data, but the prediction is noisy and unreliable, which will reduce the segmentation performance at the pseudo level. In this case, as shown in the top right figure, our USSE evaluates the reliability of the SE prediction with the uncertainty, thereby filter out the pixels with high uncertainty and only reserving the reliable results. In addition, as shown in the bottom figure, the USSE specifically designed a multi-scale uncertainty estimation, which introduces multi-scale tensions to increase the observation uncertainty. thereby improving the evaluation accuracy to the prediction reliability and promoting the robustness and effectiveness of USSE. We validated our method on a liver image dataset, and half amount of training data is box level labeled. According to the visual segmentation examples on the third row, and you can see some tumors are quite small, and compared with the enhanced image on the first row, some tumors are barely visible in the non-enhanced image on the second row. But our method has the capability to identify and segment them accurately. Compared with fully supervised state-of-art and baseline methods, our results approaches or outperform them. Here is the quantitative evaluation result. With the same amount of pixel level labeled training data, our method outperforms these methods by extra utilizing the box level labeled data. With a half amount of pixel level labeled training data, our method approaches these state-of-art methods. We also did a small experiment to evaluate the effectiveness of DDRL compared with the state-of-art DRL method, software extra critic or SIC. Our DDRL improved the tumor proposal accuracy by over 10% in IOU. This proposal improvement increases segmentation accuracy by over 15% in DICE. In conclusion, for the first time, our proposed method successfully segments liver tumors from non-enhanced image in a weakly supplied manner. It is a safe candidate computer assisting tool for radiologists due to avoiding the injection of contrast agents. It also reduces the need for manual delineation of training level. The proposed DDRL innovatively incorporates two agents to locate the tumor jointly, providing a novel solution to apply multi-agent DRL in medical object detection. The proposed USSE creatively integrates self-assembly with uncertainty estimation, offering a new method for weakly supplied medical object segmentation. In summary, we successfully integrate DRL with DL and achieve superior performance in two typical and challenging medical object detection and segmentation tasks, namely retinal body detection and segmentation, which has special anatomical structures, and the liver tumor segmentation from non-enhanced image, which has no special patterns. These works illustrate the competence of DRL in medical image analysis and inject new ideas to this field. The proposed frameworks and the models offer researchers new solutions in anatomy modeling, non-contrast enhanced image analysis. At present, we are extending DRL to multi-modality and improve tumor detection performance. In the future work, we plan to employ multi-agent DRL and modify the network for 3D image applications, thereby enlarge the generalization of DRL in medical image analysis. Finally, I want to thank my supervisor, Dr. Zhuli, and my advisory committee members, Dr. James Lesfield and Dr. Ali Khan, my features examining committee members, Dr. Aaron Finster, Dr. Ter Peters, and Dr. Boy Wang, as well as the members of the Digital Image Group of London. Here are some references. Thank you for listening.
Thank you. And actually, we have a couple of questions from the audience. And if anyone has questions, they can raise their hands and type the questions. The first question is, could you expand more on why the sampling is adaptive and how does this improve the learning efficiency?
Okay, this is a very good question. Okay, let me see. I did a small slide. As you can see, this is a regular experiment reply, right? So we store every state action, next state reward, right? This is experiment transition. into the extreme pool and sampling randomly, right, to train the agent network. So in our method, we evaluate this action is valuable or not with the accuracy improvement. And here is a threshold. This threshold is adaptively increasing as the training period. At the same time, we use unbalanced sampling from these two ports to sample the training data. And alpha is a hyperparameter. And this hyperparameter adjusts the rate that the advanced experiments is sampled. So this is the workflow of the detail about our adaptive sampling experiment supply.
I have several questions. Could you go back to the first paper? I'm not sure I understand your reward functions.
Okay. Here.
Yeah.
Oh, here.
How do you calculate these stuff?
Sorry, could you repeat it again? How to character?
Your reward is RST, right? This is equal to E beta the IT. What is IT here? Is intensity?
Sorry, I couldn't hear it clearly.
No, what is how do you define these reward functions?
Oh, how to define this reward function? Okay, the more detail is here actually. So here is the reward function. So the delta is the proposal improvement caused by the action, and if the proposal accuracy is improved, right, the delta is larger than 0. So the reward value is this one. But if it doesn't, so just put it at 0.
What is the data here?
The delta is the proposal accuracy improvement caused by this action.
Is it the global measurement or what?
You know, in every state, the box, right? The box covers,
Yes.
yeah, covers an area, right? And we can calculate this area, the overlap between this area and the target vertebral body, right? So
Yes.
we use this overlap as proposal accuracy, right? And when there is an action, it transforms this box, right, to a different location and to a different size, right? We can get a new proposal accuracy. So this is the delta means.
But in that case, in practice, okay, that means your data is small.
Yeah.
It's
Yeah.
small than equal than 0. Your reward is 0. Only the total number of the I primes is better than I. Then you get to improve the results, right?
Yeah. Yeah.
But how do you select the beta? You just
the beta.
Mhm.
The beta. So based on our assumption, we will sum this formula, right? And to increase the improvement, we have to guarantee the beta minus this eta is larger than 0, right? So actually this whole, we don't know this entire, this whole hyperparameter. So we just adjust this beta hyperparameter until the result is best. And I remember when this beta is, I remember is 0.25. Okay, I can double check it in my paper if you are interested about this, to tell you the detailed value of beta.
But here your state function, that's the e to the power the minus the eta, right? But
yeah, we sampled it, but we don't know eta, right?
yeah, you don't know eta, you don't know the beta.
Yeah, but once we want to, but what we want is the beta minus eta larger than 0. So we just try to, try different beta value to see the experimental result until
But
the
beta here, your beta here is not quite important. The most important is the beta minus eta.
yes, but we cannot adjust the eta because we don't know it. So we just adjust beta to get the best result according to the experiment.
But I'm not sure how do you get to this the following part. You said that the argmax of this one equal to the maximum sum of the IT. How do you get that?
Pardon, sorry.
The last line of your equations. The first one you said that this product of this P and R proportional either IT. That's not, is it correct? I'm not sure this is right in the math.
Yeah. It's not totally correct, but because it's not the point of our work, because we just find that it's negatively related to the accuracy. This one we can prove it, but this is just an assumption. I know the correct solution is to sample from the experiment to validate this assumption. But our work is for the segmentation and detection. This is just a small point in this work. So we just add this assumption, and the result is good. So
no, that's okay. I'm just curious, because your last row here is that correct? Because that's should be expansion of the ITs. This doesn't equal to the sum of the ITs.
Okay, here I have a small deviation. I can show you. Maybe you can address your confusion. Oh, sorry. Okay, here is the proof. So in every step in the episode, right? The possibility of ST equals the P ST plus minus 1 times the P action, right? So for the whole episode, we have this formula, right? From S1 to ST. And at the same time, we know the PS1 I1 is 1, right? Because it is the initial state, and the PA or P action is larger than 0, but a smaller 1 because it's related to the probability of DRL agent, right? So we can get the PSTIT. smaller than PST minus 1 until PS1, right? And for the entire training procedure, with n episode, we can get, for the PST, we can get the expectation of PSTs, right? And then according to the law of larger numbers, we can get this formula.
No, and what do you mean? What is the S star here? I don't understand it. The law of the large numbers, basically your conversion to expectation of that.
So, no, the PST, right, is always smaller than 1.
Yeah, doesn't matter. It's when you use law of large numbers, you get the expectation of that. That's what the law of large number means. Okay, that's fine. I want to read your papers. Regarding to your second part, you mentioned in one place, that's the two equations over there. Could you go to another page?
Sorry, which one?
There's a page, the second paper. I think that's the kinds of loss functions over there. Yeah.
Yeah.
For this paper, what is your reward function for this project?
I remember it was the same as the first paper, and
Your second paper one, you're still doing segmentation, right?
Yes. So we propose the object first and then segmentation.
You compare with all the existing literature on the segmentations, and like using UNet or other kinds of the whatever net for the segmentations. What's the key advantage of using the deep reinforced learning type of method?
So could you repeat again? Why I didn't use any deep reinforcement learning method? That's a good question, because there is no other, deep reinforcement learning method in this field.
No, you put it this way, because when you do the segmentations, the number one issue is you need to have good data set with the good annotation results, so that you can train a model that's reasonable, right?
Yes.
And I think that most of these days, the neural network have become much more complex. And actually, the improvement I didn't see too much these days. And for many of these methods, the improvement is just a little. The one thing I still thinking about, why do we need to use the deeper reinforcement learning? Because the good things about deeper reinforcement learning is because you try and basically you learn something, and then you get some improvement, right?
Yeah.
And I'm just thinking about if I compare with all the existing neural network type of models like UNet for segmentation, and how much of the deeper reinforcement learning really gain by using that. Okay, if your data is the fixed, you have an annotated data set, according to your opinions or your experience, and given that a large data set, I have all the annotation results, and then my deep learning maybe method without using the deep neural network reinforced learning, maybe reach about a certain level like 80% accuracy. And but if I using DRL, you think you're improved to another levels, or what do you think?
This is Shuo. I perhaps able to put some light in this question. So the reason we use deep reinforcement learning is because this is a very special application where we want to, as Dong just mentioned, to detect cancer or tumor in the non-contrast enhanced image. Dong, can you go to the framework page? So that show that there's two images, contrast and non-contrast. So in the contrast, yes, in the contrast image, which is the enhanced image on the right side, which is the clinician currently use, they can people or anyone by training can see visually this tumor very clearly. But on the non-enhanced image, you are not able to see it. Human is not able to see it. So now deep reinforcement learning gives us an advantage that we are able to do step by step, more like learning. That's why he put the we put the student and teacher model. Don, can you turn to the page where there's a framework for teacher and student model? Yes, the next one. So basically there are two deep reinforcement learning systems. One is in the teacher system. The teachers is looking at deep reinforcement learning to detect the tumor on the enhanced image. It's like in the real teaching environment where the teacher has the ground truth. The teacher has a standard answer, a question for all the questions. The student don't. Student can only work on a non-enhanced image where he's really not sure where is the tumor. But when the teacher slowly navigate to the area, and student could not see the enhanced image, but he can see the way they move to it there. And slowly the student would learn, oh, this is the area that teacher wants us to see. That then slowly he is able to learn using the strength of the deep reinforcement learning, learn how to detect those tumor on a non-enhanced image where the tumor is not clearly seen. While UNet or other net is able to detect the tumor on the non-enhanced image, as you said, one network is perhaps better than others, but there are not much improvement over the existing ones. But this is a very special application we are detecting on non-visual, is what we call a non-enhanced image. Hope that answers your question.
Well, you have to train this model, right? You have to have the pair of the enhancement image and the non-enhanced image in order to train this stuff, right?
That's
then you
right.
apply to the new kinds of non-enhanced images so that you can see the improvement. That's my understanding. Is my correct?
Yeah, that's correct. So in the testing scenario, the student will work alone, like in a real life. Student will work alone. Student will not have a standard answer. He will only have non-enhanced image, as you can see from on the left side. And he's still able, the key here is only rely on this, based on the training from the teacher, he's able to find the tumor, which is on the right side. This time, he has to do it alone without the teacher's help.
In your application, how many pair of these enhanced and non-enhanced images when you train the model?
200 patients, but it's a 3D works, so we convert to 2D, and almost 1,200 images, and the enhanced image and the non-enhanced image are corresponded one by one.
Okay. But how big the tumor is?
Okay, I can check the paper.
No, I'm just, I'm curious because for most of the medical image analysis, the one of the critical issues I always have is basically we don't have too much annotation images. Okay, the images with annotations.
Yes.
And therefore, if you do you believe that if you based on the 20 subjects, they really can train a model, and it really works in practice. There's some people publish a paper recently talking about the COVID stuff, right? Then there's all the paper published in the top journals. They claim they can do this stuff, but in practical, in clinical aspect, you don't have this good death. You find that all these algorithms have problems. What's your opinion about that?
I perhaps can give some answer to this one. In the medical image analysis, we always need more data. We always know that more data is more reliable than the less data. Sometimes it's not possible in the perhaps the representative example would be from your just mentioned the COVID thing, right? I don't want to comment on that one, but in our real application, we consistently find that we needed to have more data. But when the data is not, do we really need 1,000, like a 10,000 to 20,000? Sometimes we find it's not. On the top of that, we find that deep reinforcement learning, because it's a step by step, it helps us to reduce the requirement or the need of large number of training data. And as Dong just mentioned, we did not use 3D, and we use 2-dimensional. That's actually one of the way to enlarge the training samples, because every patient is a 3D volume, and when we use a 2-dimensional slice, and each slice can be used as a training subject, training sample, and then we actually increase the training sample to 1,000 level. So with this level, we can say it's if there's this possibility, we would definitely need more, want to have more data. But we consistently find that at this level, we're able to get a more reliable data, reliable results. So, and we also check around the state of art. We find that people at around 300, 500, or few hundred patients, a few thousand, those kind of image slices, is able to provide a very reliable results already. So I don't know whether that answers your question.
I agree with you. I think I think it's not just the number of the good images you have. I think there's really the issue is I think is the number of good annotated images you have.
I fully agree with you.
I think that there's many papers published in the field, and I think that the one major issue is we know that there's a lot of confounding factors behind all the image analysis. When you have the different scanners, and actually that's even the same subject, we have the large variation could be, right? And also this depends on how the distribution of the like tumor regions and across the subjects, because for some subjects the tumor is tiny. Of course, we see a lot of false positive for many kinds of imaging related to research and also in clinics. And I think the main things to me is for these models, and there's the different people are doing different architectures, and then you improve a little bit for a given data set. But if you move on to another data set, and the improvement is just gone. I'm not criticizing you. Actually the same thing for the machine learning method. I recently apply all kinds of the method in the literatures, supposed popular methods, to these kinds of simple prediction problems. Okay, I use imaging data to predict clinical outcomes, and I find that many people, they work on relative small data set, about 5 or 10 years ago, and with the method about less than 1,000 subjects, right? And they claim this A and claim B. There's a lot of papers on this topic, but when I try to using UK Bank data to do it, I have tens of thousands of the subjects, right? But when I apply all these methods, I find out most of the methods is not as good as just the simple linear models. Okay, and that's what I'm finding. That means that then most of the papers published in the last 10 years is not as good as the even simple linear models. And what's going on with this? That's And I think that then in the field, I think that we do need a larger number of data sets. Another thing is we do need a larger of a second annotated data set, just like ImageNet, because you have kinds of ground truth. Okay, and then give it a platforms, people competing on that. Okay, that's make the whole field move. I think in the right directions. Okay, and to challenge yourself to really can evaluate which method is good, which method is bad, and we should be using which method. I think that's, I'm not a comment on you. I think your stuff is good because I like this kind of way doing the deep reinforcement learning and stuff, because you try to improve yourself consistently, right? And that's important. And but I'm generally just talking about medical image analysis.
Well, I fully agree with you. The challenge to for the medical image analysis area is the variation of the data. So the generality of the of our medical machine learning system has consistently found it's not as good as we expected. There are two reasons for that. A is usually we have a very small data set to work on, and B is also the nature of the images we have. Because for example, the MI image is not an absolute value, not like a CT image is an absolute value. Because the magnetic field it has, every time the image, even the same patient, even you scan twice at the same time, the image value, the gray level value of the image pixel will be different, right? So because the MI is looking more relative value rather than absolute value. So this defines the variation of those images will be much larger than those natural images, so which is understandable. But we still manage to prove the concept. We find that as you said, we are able to improve the algorithm within the data set we have, and slowly also, as you suggested, we start to grow our data set, not just by ourselves, but also by the community. So we have our group used to work on hundreds, now we have several hundreds. The community also consistently provide the open data set. And so we, for this tumor project, we don't have the cross-center data, but for the spine project, all the data are collected from globally, meaning that the researcher from different institutes would contribute to share their data. And when our students work on those spine projects, the data actually from multiple places. We consistently find that when we have all this variation already included in the training data set, our system become more and more robust. So we are not moving as fast as we want to, and certainly not as fast as you want to, but we are moving towards the right direction.
Maybe someday you can create a kind of image net for medical imaging analysis. I think that's would be a huge contribution to the field. But otherwise, everybody claiming, like it, right?
We do have a similar, for example, we call it SpineNet, the one I just mentioned. So everyone in the world is able to share their data, and the people, as I just mentioned, the spine community would share those data from I think at least 10 or 15 or 20 groups. When they finish their research, they put the data on the spine web, which hosts on our server. So we do have those open shared data. It just the labeling in the medical area need to have certain qualification. We can't just use the Fifi list method, put online and let everybody label it, right? So as once again, get back to the concern you raised, high quality label is so difficult to get. So even you have the images, you don't have a high quality label, meaning that you have to have several radiologists willing to label it for you. That has been found a consistent challenge in our field. But once
No,
again,
I sometimes I don't trust the MD doctor in the annotation results.
exactly.
We did it for some of the, one of my collaborators, basically they asked the graduate student from Stanford, the whatever in which department, basically ask them to do annotation. Actually, the variation, even for the same subjects, the variation, the results totally inconsistent.
I agree.
To be honest with you.
We actually have a stats from those studies, so no problem. I have no problem to understand it. But while we are moving on the machine learning side, we also work on the labeling side, because this intra-observability is consistently a challenge for us. That's why the medical image analysis is a little bit unique and a little bit challenging, but also very interesting, because while those intra variability is there, the doctor still seems able to reach a consistent diagnosis and treatment. So we are working on this, and hopefully in the near future we find that those labeling is important, but not the precision of the labeling, maybe not that important when we put it into a large data set, when we put it in the large labeling, but that takes time, especially in the medical area. The accessibility of the data is challenging, labeling of the data is challenging, so it takes more time, but we are certainly moving towards the right direction.
Yeah, maybe ask Dingong to do some annotation and share with other people.
That's a good plan.
He has money to do it. Okay, and finally, thank you my friend and his student, and for a wonderful talk. And thank you.
Thank you very much for the invitation. Thank you.
Thank you.
Thank you. So I will end the meeting now.
Thank you. Bye.
Bye.
Oh, thank you.
Thank you, Dr. Lee.
Bye.
Thanks for the cheer.